All right, how's everybody doing today? Oh, that's right, you can't talk back. Sorry, redundant question then. All right, hello everyone. Welcome to my webinar on how to write a good vertical turbine specification. Let's go ahead and get started. So if your connection drops during this webinar, just please use the link to log back in again. And I'll answer questions at the end. You can submit questions using the built-in Q&A feature within Zoom at any time during the presentation, and I'll cover them at the end. So quickly about myself, my name is James Schumacher. I'm the sales engineer for Oklahoma and the branch manager for the Fort Worth office. I started as an application engineer back in 2008, and I've worked on hundreds of jobs with vertical turbine pumps. So I've reviewed many preliminary specs, and I'll cover common issues found. I'm legally required to tell you about Smith Pump, so I'll keep it brief. Smith Pump started in 1962 out of Waco. Waco is still our headquarters today, with branches in Fort Worth, Austin, and Houston. We cover all of Texas and Oklahoma. All locations handle sales, service, and repairs. However, Waco specializes in manufacturing and engineering, while Fort Worth has motor rewind capabilities. The top row of pictures are examples of repair and fabrication. The green pipe in the top middle is a fabricated column pipe for a vertical turbine. We have on-site technical services for pump removal and installations, a UL listed control panel shop for panel construction in Waco, and all facilities include warehousing for pump parts. The Waco facility is our primary manufacturing location. Our fab shop has state-of-the-art tooling, and we can repair and recondition pumps to meet or exceed OEM specifications. So today's agenda will be broken into two main parts. The first is planning a design before spec is ever written, and the second part is common issues found when Smith Pump reviews the spec and how to correct them. We'll end by reading your questions and trying to answer your questions. I've been told this presentation is informative but unexciting, kind of like my personality, but I'll do my best to keep you awake. All right, so this all starts when an owner approaches the engineering firm with a problem. Sometimes the owner's waited too long and population growth is predicted to exceed current water supply. The owner feels like the picture where imminent disaster is at hand unless the design firm can find a solution. So planning all starts with an immediate need or future need from the owner. Some of the first questions asked are, what are the owner's requirements for today? What about in the future? How long will the station be in service? These questions are the starting point for pump selection. Other factors that determine pump selection are where the pump station is located and how water is moved in and out of the station. Are pumps filling a local tank or pushing water miles across town? How much space is available at the pump station? So these decisions affect pump type and pressures required. Once a firm station capacity has been determined, a system curve is calculated. The curve is a combination of static lift and friction loss through piping and valves. Results are combined in the pump station system curve. Just like that. This system curve will tell us the pressure required to meet a certain flow rate. In this example, a station firm capacity is 4,000 GPM. Pumps will need to produce around 160 foot of head to meet the capacity. Once a station design and system curve is known, it's time to find a pump. Of course, we're going to focus on vertical turbines for this webinar, or the title will be very misleading. Well, how many pumps are required to meet a design condition? 1, 2, 5. This is the point that Smith Pump typically starts working on pump design with the engineer. We generally try to use the least amount of pumps to meet the capacity, but ultimately the budget helps us determine whether we pick lots of small pumps or a few large pumps or somewhere in the middle. So back to pump station design. Does the application or owner want equipment indoors or outdoors? Luckily, pumps can go in either. The type of motor enclosure is the only change between the two. If inside, remember to include an opening for future removal. Don't encase a building around the pumps and trap them like this cat. We've removed pumps stuck inside buildings, but it's much slower as equipment is disassembled piece by piece. Typically, an external crane will do the heavy lifting of installation and removal through a roof hatch. Station design and piping layout is important. It determines if the job requires barrel-mounted pumps or wet pit-mounted pumps. Good practice can be correlated to longer pump life and easier maintenance. Let me show you 3 ways poor piping layout can reduce pump life. Oh, and a side note on this picture, I wanted to mention that there's lack of proper footing under this pump, and Smith Pump would have installed a concrete pad under this flange for support, just in case you notice that detail. The first way to distort the discharge head is pipe strain. Have you ever heard those dirty words mentioned before? It's when 2 pipe flanges that don't align are forced together. This can cause serious damage to the pump. So when it comes to pipe strain, I tend to think of pumps like they're made of rubber instead of steel or cast iron. It's because pipe strain can actually bend and warp the pump case or discharge head on vertical turbines. This throws the line shaft out of alignment and causes reduced bearing life and seal life. Here's the second way to distort the discharge head: loading the flange with too much weight. Piping supports are crucial to a pump's life, especially vertical turbines. The perfect piping setup bears no weight on the pump flange and has a flexible coupling for perfect flange to flange alignment. The picture on the left shows no pipe support, so the pump has become the pipe support. The drawing on the right shows a pipe support, but it's too far away. These pumps are bearing most of the valve weight, and valves are heavy dudes. So here's some improved piping support layouts. The bottom shows improved pipe support, but more support should be added to reduce the flange loading. It has a flexible coupling to reduce pipe strain from misalignment, which is good. The top drawing anchors all piping near the pump for maximum support. This allows the concrete block to support the pipe weight, not the pump. Final flange to flange alignment requires field welding the pipe in this example. Since field welding is somewhat impractical, the bottom picture is more commonly found at job sites. The last way to distort a discharge head is from its own pressure. When a pump pressurizes the discharge line, it pushes the head backwards, like the exaggerated picture shown there. Thrust blocks and thrust rods should be used to keep the pump head stationary. Again, if the head moves more than a few thousandths of an inch, it pushes the shaft out of alignment. This leads to poor bearing life and reduced seal life. We have seen inadequate thrust rods used and still allowed the pump head to move. The AWWA standards for thrust rod sizing is typically not sufficient for pumps, so we tend to upsize them. The bottom is an example found at a job site with only 1 thrust rod used. We replaced this pump for a larger unit and installed at least 4 thrust rods. I believe we actually went back and put more thrust rods on these pumps after testing, but I couldn't find a picture of that installation, so we needed quite a few more. So let's talk about the 2 vertical turbine pump arrangement options, barrel and wet pit. Barrel mounted pumps can draw water from above grade or below grade, depending on the piping setup. These pumps have a few advantages over wet pit pumps. They have a smaller footprint, generally less expensive to excavate, and are cost effective. However, they do have less storage volume and require a separate water storage tank to feed them. The barrel must be installed plumb for maximum pump life, and barrels have a specific design requirement by the Hydraulic Institute standards that should be followed. Wet pits are great if you want to combine your storage tank with your pumps. Prepping a firm level surface for setting pumps is easier on a wet pit. They only need a sole plate installed and leveled, as opposed to leveling the entire barrel unit. We also recommend keeping concrete hole as large as possible for future upgrades for larger equipment. We have seen upgraded equipment not fit through the concrete hole before. and I want to quickly cover 3 options for starting a pump. The first and most common is across the line. Line power is directly applied to the motor. You only get one speed, but it's the least expensive way to run a pump. Another method is the soft start. It provides a general ramp up to full speed. So here's my metaphor comparing across the line start to soft start using one of America's favorite pastimes, the drag race. Across the line starts are pedal to the metal and somewhat violent on the electrical system due to inrush current. It gets the pump up to speed in a hurry, but pulls as much as 6 times the nameplate amps momentarily. However, a soft start controls or limits the voltage and slowly ramps up to speed for less shock to the system. Just like the blue and red car, they get up to speed in a slow but comfortable rate. And finally, the VFD. The variable frequency drive allows for variable flow. They can save money operating at reduced speeds, and they also act like a soft start. They work best on systems with high friction losses. However, using them on a system with high static head, like this one, doesn't allow much turn down. This example can only use about 85% to 100% speed range, so an investment in a VFD may not be worth it. All right, so let's jump into the main reason for this webinar, how to write a good spec. So first I want to show you an example of a poorly written spec that lacks the details needed to bid. The pump guys may assume the writer's intent, but we all know what that means. Typically has a lot of questions they're asked and email starts flying. Addendums begin to mount. Have you seen a bid with 12 addendums? Because we have. Ultimately, a poor spec will get equipment to the job site, but it could be different than imagined. I give that cake blob a C for effort. So when reading the spec, the first thing the pump suppliers look at are the duty conditions. We want to know the primary rating, the secondary ratings, efficiency, operating range, and so on. Sometimes we find missing elevations in the spec or plans. Key elevation requirements are the discharge center line, the final floor, typical start and stop points, low water level, and floor elevations. If using a barrel mounted pump, define the gravity supply tank's high and low elevations. These levels help us determine pump length to meet MPSH requirements and minimum submergence levels as shown here. Without getting into a pump hydraulic class, we need to know the elevation at which the specified head was calculated. There are typically 2 points, the low water elevation or the discharge center line. It matters because the pump has to produce more head than requested if the TDH is based from the discharge center line. You can see the extra static head elevation the pump must produce from the red arrow. And I brought this up because Flowserve has a sophisticated pump selection software called Affinity. It needs the correct elevation to make accurate selection. So let me show you a quick behind the scenes look of how the Flowserve software does all these heavy calculations. I don't understand their methods, but I do know that elevations are important for a good pump selection. Forgetting to list the material requirements is like playing the lotto. If materials are unspecified, you'll get the manufacturer's standard material, which could work for the application or it might not. 2 very common upgrades we normally recommend are hardware and shafting to stainless steel. These items are typically standard in carbon steel for most manufacturers. Sometimes carbon steel shafts corrode enough in service that they must be torched off during disassembly. So at that point, we just replace them with stainless so it doesn't happen again. And let's jump into more common things we find when reviewing a vertical turbine spec. Sometimes we see requests for field vibration to be less than Hydraulic Institute published values. Almost any vibration level can be achieved in the field. The cost to hit that may be substantial. All field manufacturers design their equipment to meet current HI vibration level. Some manufacturers will not bid the jobs if asked for vibration levels less than HI. Others will bid at a premium price to cover themselves. In 2009, HI updated their vibration standard tighter than the current API or ISO vibration standards for vertical turbines. This allowed field vibration on motors larger than 268 horsepower. The allowable field vibration on motors larger than 268 horsepower is 0.17 inches per second. It's kind of hard to read there. I'm told that somewhere around 0.3 inches per second, which is here at this line, is the maximum limit a pump can operate continuously and still have a good lifespan. So unless the application requires extremely low vibration, we always request 100% vibration levels to be used. We have seen some specifications note that only the pump manufacturers such as Flowserve can produce the equipment and not pieced together by the supplier. Smith Pump agrees with this statement, as the reasoning behind the statement is to control quality of the entire pump. We don't want someone in the garage fabricating parts like this one. They may believe it's good to go, but the owner may have a different opinion. Since Smith Pump is a manufacturer of VTP components, we've gone the extra mile to become ISO 9001 certified to provide quality products and services backed by a quality management system. Therefore, we typically ask if the supplier can manufacture parts only if the supplier is ISO 9001 certified. So Smith Pump is actually currently ISO 9001 2015. We're up to the 2015 standard right now. So it looks like our flag needs to be updated. I could tell our quality manager, but she'd probably have to write a procedure on how to change the flag before we could touch it. That's just a bad ISO joke for anybody that's ever worked for an ISO company. Sometimes we see a spec ask for a specific barrel ID. While it can be done, the cost associated may not be worth it. When making a suction barrel, we use plain Jane regular old pipe during fabrication. Any pipe larger than 12 inches sold by the outside dimension, not the inside. So let's take a 30-inch pipe, for example. If the OD is 30-inch with 3/8 wall, this makes the inside diameter 29¼ inches. If the spec wants a 30-inch ID barrel, we have to roll plate to make a 30-inch ID barrel. So be aware the added cost for this extra 3/4 inch ID typically isn't worth the rolling and welding cost on small pumps, but it could be justified on larger equipment. The levelness of equipment is also crucial to bearing life, vibration, and overall equipment life. We want to see the sole plate or barrel top levelness specified as 0.02 of an inch per foot or less. Barrel plumb should have a maximum lean of about 1/16 of an inch per 4 foot, which works out to 15,000ths of an inch per foot of height. When specifying an NSF pump for use in potable water, it needs to require proof, such as a nameplate on the equipment. The manufacturer should supply some sort of documentation at submittal time stating this particular product has been NSF 61 certified. The equipment should have an NSF nameplate on it as well. So meeting the intent of NSF or using NSF approved materials in lieu of the real NSF certificate should not be allowed. If materials are not certified by a third party, the owner has no proof of how safe the pump is for public drinking water system. And even coatings are NSF approved. We always recommend using an NSF rated coating when using a potable water pump. The Tanemic data sheet here shows their N140 epoxy system is NSF 61 certified. So forgetting to add spare parts can be very costly later. During manufacturing, the machine setup is set up to cut wear rings, the impeller, the shaft, and the bearings. So asking the facility to generate a few spare items while manufacturing the pump is the least expensive time to purchase. Purchasing later is more expensive, due to finding the original blueprint, material sourcing, the machine setup time, and extra shipping costs. So Smith Pump always recommends a basket strainer with the built-in vortex presser on all turbine pumps, whether barrel mounted or wet pit. They serve two purposes. One is to keep stuff out of the pump that doesn't belong, and the other is to reduce pre-swirl and help correct the fluid approach angle. So here are two examples using the plate baffles on the left and vane grading on the right. So always request a basket strainer with a built-in vortex suppressor made from stainless steel. Wear rings are a great addition to a pump spec, but not all pumps can use wear rings. Only the enclosed impellers can utilize wear rings because their design has a landing on the suction side for the wear ring installation, shown here. Semi-open impellers seal between the vane and the bowl, so there's no place for a wear ring to be used. So here's a quick side note on the advantage of the semi-open impeller. They seal against the bowl on the vane edge, right there, with a very tight tolerance. Because of this tight tolerance, the resistance to recirculation, they're typically more efficient than enclosed impellers. Over time, this edge wears and the tolerance can open up, but it's okay because restoring the tolerance can be done from the surface without even pulling the pump. Adjusting the impeller at the motor restores the clearance back to the original tolerance and efficiency. So we recommend wear rings, but remember they're only for enclosed impellers. Not all pumps are created equal, and the same goes for impeller materials. Always specify a suitable material for the application. Shown are the before and after of a severe erosion on this impeller. The standard impeller material for most vendors is some sort of bronze alloy. The standard bronze alloy is good for most applications, but may not be good for your application. If there will be corrosives in the fluid, an upgrade to stainless steel could be worth it. If cavitation is expected due to insufficient MPSHA, an upgrade to nickel aluminum bronze could help the impellers last much longer than the standard bronze. Nickel aluminum bronze is a good choice for withstanding cavitation and erosion, but if in doubt, just ask the pump supplier for their suggestion. Bowl lining is a fairly standard practice in the vertical turbine world. So lining a bowl serves two purposes. It smooths the casting walls to increase efficiency. It also protects the bowl from erosion and corrosion. Typically small bowls, somewhere around 20 inches or less, have their interior water passages coated with porcelain that's baked on for a hard but smooth finish. It's the same finish you see on a toilet or a porcelain sink. Larger pumps may not come with any coating as standard. So this is when some type of Belzona, Super Metal Glide, or 3M Scotch coat should be specified. So always ask for a bowl lining when writing a spec. Keyed shafts are a great way to transmit torque between two rotating pieces, which is why we normally see keyed shafts on motors. So if this is common practice, why don't vertical turbine manufacturers key all line shaft connections as standard? As you might have guessed it, it's mainly because of price. Threaded shafts are simple and less expensive to manufacture. They transmit the torque and resist downward thrust from a spinning impeller. However, somewhere around the 3-inch shaft diameter, threaded shaft connections are much harder to break apart and they have a tendency to gall together. So this is when the more expensive keyed line shaft is typically needed. Speaking of difficult things to take apart, let's talk about column pipe. Threaded column pipe is the least expensive method for joining column together. However, it should be reserved for small pumps only. We recommend avoiding this method when column pipe is 10 inches or larger and switch over to flange pipe. Threads can rust together and become very difficult to unscrew during disassembly. If that happens, we break out the torch and remove the offending section. It ruins the column pipe, so it's not a preferred way to take apart a pump. Mechanical seals have become popular seals over traditional packing, but sometimes major details are missing, such as the type of seal or materials of construction, or even the seal flush plan. Turbine seals come in two main flavors, cartridge and split. Cartridge seals are known for their reliability and leak-free design. However, split seals are gaining popularity for their ease of replacement. Remember to specify seal face materials suitable for the application. Typically, soft faces are used for clean water and hard faces for dirty water. And we also always recommend a seal flush plan to be used with the mechanical seals. A plan 13, as shown on the far right, is typically used on vertical turbines. This piping plan allows cool water to flow past the seal faces and carry away heat. The heated water is returned back to the suction barrel for repumping. So speaking of seals, let's talk about motor and seal compatibility. Motor and seal choices have a direct relationship with each other, and they're not 100% interchangeable. Take a look at the green chart here. Packing is acceptable to use on both a vertical hollow shaft and vertical solid shaft motor. Why is it we can't use just any motor on any seal? It comes down to shaft runout. So runout is the amount of movement the shaft has in the seal area. So here's an exaggerated picture of the shaft movement if viewed from the motor side. The top picture shows the shaft runout measured with a dial indicator. So our general rule of thumb is shaft runout no greater than 0.02 of an inch per foot when using mechanical seal, or 0.005 of an inch with packing. A vertical solid shaft motor begins with less runout because it has a lower bearing close to the seal, shown right there. The pump shaft in a hollow shaft motor runs in a tube. So this tube is the rotor shaft. It has supporting bearings on top and bottom. However, the pump shaft does not have a lower bearing to restrict shaft movement. Therefore, the shaft has a potential for higher runout values. In summary, use a solid shaft motor if using a mechanical seal. The motor coupling is also related to the seal type used. If using a mechanical seal, we recommend using a 4-piece coupling. While a 3-piece coupling can be used, the motor would have to be removed if replacing a cartridge seal. So a 4-piece coupling does not require the motor removal because it has a spacer section shown right here. Removing the spacer creates a large enough gap for the cartridge seal to slip out. It's a huge time saver for seal changes. And we recommend space heaters to be used on every motor sold. It's inexpensive insurance for long-lasting motor. Space heaters, or anti-condensation heaters, are installed to prevent moisture condensation within a motor. It's typically energized while the motor is in storage or when the pump's not running. They work by keeping the internal temperature of the motor above the ambient dew point. They typically run on 120 volt power and are sized by the manufacturer according to the motor mass. You can check if a motor is using a space heater by feeling the outside housing with your hand. It should be warm to the touch, but not hot. Testing space heater function on motors is an experiment I recommend you try next time you're at the job site. However, I don't recommend trying this experiment at the job site. Can I reach the ceiling without proper tools and cheating death? Maybe you can. I don't plan on trying that. So let's talk about equipment spacing. This can easily be overlooked when trying to squeeze all the equipment into the smallest building possible. The above pictures are good examples of future headaches waiting to happen. Problems related to heat, vibration, and maintenance can occur. Here's an example with better spacing layout for heat, vibration, and maintenance. So motors blow air to cool down, but tightly packed motors will draw on hot exhaust from its neighbor. Excessive heat buildup will lead to shorter motor life. Pumps can shake the ground if the structure mass is not adequate for the application, or one bad pump could transmit vibration to nearby operating units if spaced close enough. Finally, the not so obvious issue is future maintenance. And I wouldn't want to be the maintenance guy for the 5 units packed this tight. Okay, so now we're jumping over to VFD related issues. If possible, provide a system curve and expected operating range so the best pump can be selected. If this information isn't shared, we could pick the wrong pump that still meets the duty conditions specified. VFDs have been marketed as the best way to save energy and reduce operating costs. This is true, but not for every application. It's possible to install a VFD in a poor application for little return on investment. One of the worst applications is a high static system head because the curves are relatively flat. This example shows a pump that can only reduce its speed by about 10% before it's outside the allowed operating range. So this has a 10% operating range, which is probably not the energy savings an owner is expecting. We recommend using a VFD on systems with high friction losses. It allows the pump to reduce speed and stay within the allowed operating range for a much higher turndown rate. As VFD popularity grew, so did the problems. Smith Pump found out the hard way how damaging VFD can be on motor bearings. You can see the damage that occurred on the bearing races while operating a standard motor on a VFD. Essentially, a charge will build up on the rotor until it can't hold any more charge, and it finds a path to ground. Typically, bearings are the easiest path to ground. So the electrical discharge generates a fluting pattern seen on the bearing race. I don't understand the theory on why this happens, but I do know how to protect motors from this damage. We recommend 2 upgrades on a motor when using a VFD. The first are insulated bearings. A special coating on the bearing resists an easy electrical path for charged rotor. That charge is grounded by the use of a shaft grounding ring. This ring has tiny carbon brushes that make physical contact with the shaft and is usually installed on the motor drive end. The grounding ring is secured to the motor frame and electrically connected as well. So this shows the final electrical path for safe rotor grounding through the motor frame. It's a simple yet cost-effective way to prevent premature motor failure. Without getting deep into vibration analysis, vertical turbines have a good chance of operating at or near their natural frequency when running on a VFD. So what does that mean? Take a look at this animation. The pumps can start moving like this in real life. It's a great way to destroy the equipment and scare everyone at the job site. Since cast iron heads are a fixed design, they have a fixed natural frequency. Typically, this is okay on constant speed pumps, but it runs a higher risk of vibrating on a VFD as the frequency changes. So how do we combat operating near the natural frequency when slowing down a pump? Basically, a custom fabricated steel head is made for the application. It all starts with an analysis performed by the manufacturer. We always recommend performing analysis of the pump if running on a VFD. This will let the design team fix potential issues before fabrication. So the read frequency basically determines the discharge head and motor natural frequency. The parts are modeled in 3D and calculations are run based on expected operating range. The head may need design modifications to increase or decrease its natural frequency. Some of those common changes include adding stiffeners, changing the window size, increasing the wall thickness, changing the height, or increasing the body diameter. So here's an actual before and after modeling where the window was enlarged to decrease the natural frequency for one of my past jobs. Another common analysis is the shaft critical speed. It models the entire line shaft to ensure it doesn't damage itself during operation. It's typically tuned by adjusting bearing spacing within the column pipe, similar to playing the guitar and changing pitch by moving your hand position on the fretboard. So let me cover a few quick points on pump testing. We've seen some specs ask us to guarantee multiple design points on a pump. It's usually good to see multiple points called out on a spec because that helps us pick the closest matching pump curve to the shape defined. However, the factory will only guarantee 1 point during factory testing. The impeller can only be 1 diameter, so there can only be 1 point to hit. The factory can test at multiple points, but only 1 will be guaranteed. Owner witness testing is a common adder within the vertical turbine spec. However, we have seen some language written that says the owner may be allowed to witness the testing. We agree the owner should be allowed to witness their equipment, but all costs associated with this uncertain trip needs to be covered. We recommend including a bid line item for witness testing and travel expenses. That way the owner can save money if they skip the witness testing. And we're going to jump on to the last poll. What is the likelihood of working with a supplier like Smith Pump during the next pump station design? Highly likely, a good chance, maybe stranger things have happened, or not likely. I prefer to shoot from the hip and hope for the best. All right, good. I was hoping for those. Okay. All right, we made it to the end. So here's the cliff notes on today's presentation. Design with the future in mind, specifically the maintenance and upgrades. Piping strain is bad. Use thrust blocks and pipe supports. Provide all elevations possible. I've never seen too many elevations provided. Specify a material or you will get the standard. Better pumps cost more money. Don't forget the spare parts. The seal, coupling, and motor need to be compatible. VFDs add complexity to design, but offer big payoff if done right. And a well-written spec can provide a long service life, competitive bid, and set clear expectations with all bidders. So I want to thank you for joining the webinar today. Please reach out to myself or your local salesman for help on a vertical turbine spec or anything else pump related. We love talking about pumps.